In this lecture video, we'll continue our conversation about street routing problems. Specifically, we'll extend our knowledge of graphs to the ideas of Euler paths and circuits. We have already defined the idea of adjacent vertices. Those are two vertices that share an edge. Now we'll talk about adjacent edges. Adjacent edges are two edges that share a vertex. For example, edge BF is adjacent to edge FG. They share the vertex F. A path is a sequence of edges, each adjacent to the next, with no edge included more than once, and starting and ending at different vertices. The idea is that once you traverse an edge, you cannot traverse it again. An example of a path starting at vertex A might be this: edge AB, then edge BE, and then edge ED. This path begins at vertex A and ends at vertex D. We can travel from A to D without traveling over any edge more than one time. We can describe this path a couple of different ways. We could list the edges like this, or we could list the vertices in order from beginning to end. Let's consider another path. Starting at A, we'll go to vertex B, E, and then D. But rather than stopping at D, let's travel over edge DA and end with edge AC. Let's also express this path by listing out the vertices. We started at A, then went to B, E, D, A, and C. Notice that we visited vertex A more than one time. The only thing that we cannot do with a path is travel over the same edge more than once, but we can visit a vertex more than once. The length of a path or a circuit is the number of edges included in that path or circuit. That means that our first path, ABED, has length 3, and our second path, ABEDAC, has length 5. Remember, we're counting edges, not vertices. A circuit is the same as a path, but instead of starting and ending at two different vertices, a circuit will start and end at the same vertex. Let's take a look at some examples. If you're anything like me, these graphs might remind you of puzzles you used to do as a kid. The goal here is to see if we can traverse the entire graph or trace the entire graph without picking up our pencil. We also don't want to draw any edge more than one time. Let's start with this first one. I'll start at vertex C. From C, we could travel to vertex D, then to A, then maybe to E, B, back to A, C, B, and ending at D. This is an example of a path. And since this path traverses the entire graph, it's a special type of path. This is called an Euler path, named after a famous mathematician. An Euler path is a path that covers all edges of the graph. Now let's look at this second example. We'll do the same thing. This time, let's start at vertex A. We could go from A to C, then C to F. Our only option is to go from F to D. We have a choice to go to A or B next, and it really doesn't matter. From here, we need to go to E, then to B, then finally to C, D, back to B, and then A. Notice that this time I ended up right back where I started. We started and ended at A. So this is an example of a circuit. And since we traversed the entire graph with this circuit, it's a special type of circuit. This is called an Euler circuit. An Euler circuit is a circuit that covers all the edges of a graph. Notice that the only difference between an Euler path and an Euler circuit is where we end. Euler paths start and end at two different vertices, while an Euler circuit starts and ends at the same vertex. Let's take a look at this last one and see what we can do. If we start at vertex A, we could go to B, C, or D. Notice that going to B or D is really equivalent, so it really narrows it down to two options, B or C. Let's try going to B. Now we could go to C or D. Let's try C. From here, we could go to A and then D, but then there's no way to traverse those last two edges. If we go to D and then A, we again can only traverse one of the last two edges. So let's back up. Suppose instead of going from A to B and then C, We instead go from A to B and then D. From D, we could go to A and then C, but then we're stuck. We could go to C and then A, but then we finish with edge AD without BC. Let's give this one more go. Beginning at vertex A, instead of going to B, let's go to C. From C, we could go to B or D. Let's go to B. Now from B, we could go to A and then D, or D and then A. But either way, we're stuck and we can't finish. With this graph, we have neither an Euler path nor an Euler circuit. We can also categorize graphs as connected or disconnected. A graph is connected if there is a path going from any vertex to any other vertex. Otherwise, it's disconnected. When a graph is disconnected, it consists of two or more components. A bridge is a specific type of edge in a graph. If you have a connected graph and you take out an edge and it becomes a disconnected graph, then that edge is considered a bridge. In other words, a bridge is an edge in a connected graph without which the graph would be disconnected. In this graph pictured here, imagine what would happen if we took out edge BF. There would be no way to get from vertices G, F, and H to A, B, C, D, or E. So the graph would no longer be connected. It would be disconnected. That means that edge BF is a bridge. Without it, the graph would be disconnected. To go along with our Euler paths and Euler circuits, we have three theorems known as Euler's theorems. The first one is Euler's circuit theorem. Euler's circuit theorem tells us two things. If a graph is connected and every vertex is even, then there's an Euler circuit. But if a graph has any odd vertices, then it does not have an Euler circuit. Let's look at these three example graphs below. Our first graph has two separate components, so it's not connected. So that already disqualifies this graph from having an Euler circuit. Looking at the other two graphs, they are connected. So now it becomes a question of the degree of all of the vertices. Let's start by looking at vertex A. There are two edges that meet at vertex A, so A has degree 2, which is even. There are 5 edges that meet at vertex B, so vertex B is odd. We already know without looking at any of the other vertices that this graph does not have an Euler circuit, simply because we have an odd vertex. Notice that vertices E, G, and C are also odd. Finally, let's take a look at the third graph. The degree of A is 2 because there's 2 edges that meet at vertex A. This time, vertex B has degree 6, which is even. Vertex E has degree 4, which is even. Vertex F has degree 2, which is also even. Vertex G has degree 4, C has degree 4, and D has degree 4. Since all of the vertices of this graph are even, we know that this graph has an Euler circuit. Starting anywhere you'd like, you should be able to trace the entire graph without lifting your pencil. Now let's look at the second of Euler's 3 theorems. This one is called Euler's path theorem. Euler's path theorem tells us that if a graph is connected and has exactly 2 odd vertices, then it has an Euler path. It must, however, start and end at those odd vertices. If a graph, however, has more than 2 odd vertices, it does not have an Euler path. Let's go back to the Königsberg problem and use what we've learned to answer that question. With the Königsberg bridges puzzle, the question is, can we walk across every bridge exactly one time? The answer will be yes, as long as there's an Euler path or an Euler circuit. We can use the first 2 of Euler's theorems and look at the degree of each vertex to answer the question. Vertex R has degree 3. Vertex A has degree 5, L has degree 3, and D has degree 3. Every vertex has odd degree. So we know that there's definitely not an Euler circuit. We also know that there's not an Euler path because there's not exactly 2 odd vertices. That means that we know it is impossible to cross every bridge exactly once. We can consider problem 4 solved. Now let's look at Euler's sum of degrees theorem. This theorem tells us that the sum of the degrees of all of the vertices of a graph equals twice the number of vertices. This means that the sum of the degrees of the vertices must always be an even number. 2 times anything is an even number. This also means that a graph must always have an even number of odd vertices. Otherwise, the sum of the degrees would be an odd number. Let's summarize what we've learned so far in a table. If a graph has no odd vertices, we know from Euler's circuit theorem that the graph will have an Euler circuit. We also know from Euler's path theorem that if there's exactly 2 odd vertices, then there's an Euler path. If there's any other even number of odd vertices, then there's neither an Euler circuit nor an Euler path. And all of the other options are impossible. Based on Euler's sum of degrees theorem, it's impossible to have an odd number of odd vertices. And that will conclude this video lecture on Euler paths and circuits.